So you already have two different demos of me doing this freeform timed assessment. I'm gonna do this again a third time, add to the existing illustrations. Now, in the interest of a full disclosure, transparency, I have looked at the question before. Mainly because, again, I've done this demo twice already. So if I just randomly start, there's a good chance that the question I get will be one of those two. And I think both the demos I've done, they involve the solenoid, and I have lots of versions of questions that involve solenoid in one form or another. And I wanted to do an example of a question that doesn't involve solenoid. So I had to roll the dice a few times for test student to make sure that when I click start here as test student, it'll start with a question that has nothing to do with the solenoid. So again, full disclosure, I've looked at the question, but I did it just minutes before starting this session, and I didn't have a lot of time to think about the question. So I promise this is as a genuine demo of someone working through the question in 20 minutes or so of time limit as I can make it. So with that intro, let me click start, and I think I said this before, 20 minutes is a really short amount of time even for me, so I'm gonna be careful about how much time I spend explaining things versus writing down answers and submitting something within 20-minute time limit. So with all that, let me start and get started. And I get these two parallel wires. I said I've looked at it before to make sure that I won't get the solenoid question again. Let me copy and paste this in case I need the image of it for some of the work. So, wait, can I move this? Okay. All right. Consider two infinite parallel lines of charge. Okay, characterized by uniform linear charge density. Okay, yeah, that must be the lambda that's labeled. Separated by distance d, oriented vertically with wire 1 on the left, 2 on the right. Okay. If your answer to the in terms of the given quantity physical constant, suppose that the two lines of charge both move upward. So for part A, we are describing where they move upward at speed v0. Show that the magnitude of magnetic field due to wire 1 at the location of wire 2 is that using Ampere's law. So I don't know how much justification I need to give, but with this information combined, basically what it ought to be is this wire 1, it's going to look like a current of magnitude. I think lambda v0 is right. Let me just check the units. Lambda comes in units of coulombs per meter, charge per length, and speed comes in units of meters per second. So when you combine these, you get coulombs per second, which is the right unit for ampere current. So it's probably reasonable that this is the current. So the rest of the question is basically then you have a straight long line of current of this lambda v0. What is the magnetic field at this location? What is the magnetic field? This is a classic application of Ampere's law, one of the four symmetric geometries that you can apply Ampere's law to derive magnetic field. So let me start out with the statement of Ampere's law. Statement of Ampere's law is line integral of B dot dl, and there's something special about this line integral. It's around the closed loop, the Amperian loop that I'm going to be choosing. That line integral is equal to, let me try to remember this, 4 pi ke over c squared times I enclosed. Or in the more traditional combination of constant, traditional combination of constant, it should be equal to mu naught I enclosed. I'm trying to keep using Coulomb constant and speed of light as much as possible. I'll explain later. So I'm gonna stick with this version for the rest of my solution. So that's Ampere's law. That's a statement of Ampere's law. Now, in order to apply it, you need to have a loop in mind. And since we are trying to find the magnetic field here, the loop that I'm going to choose, it must include that point. So I'm gonna choose a loop that kind of follows the symmetry of the setup, which is a cylindrical symmetry. So if I go in circles like this, then it includes this point. And I have from application of right hand rule, I have some sense that magnetic field wraps around the current this way. So on the right side of the wire points into the page, left side comes out of the page. So magnetic field goes in, comes out. This is my sense of the magnetic field. And from the rotational symmetry, ignoring wire 2, just wire 1, from rotational symmetry, magnetic field here should be magnetic field here, magnitude, same magnitude all the way around this circle. So all of these facts I need in order to do this next step. So this B dot DL, I'm gonna simplify that as simply B DL, because the direction of magnetic field and direction of my the loop, the Amperian loop. So let me label it Amperian loop. It's in the same direction. So the dot product just gives you 1. So BDL. Now from here, I'm going to make the symmetry argument. So from cylindrical symmetry, say that magnetic field is uniform around the loop, so I can pull it out of the integral. So doing that, I get B line integral of DL, and this is the magic of symmetry. I know what this is. This is integral of this line segment around this circle of radius D. So this should just be 2 pi D, the circumference of the circle. So putting all of this together, you have left hand side simplifying as magnetic field times 2 pi D. On the right hand side, you have the combination of coefficients, 4 pi k over c squared times the current enclosed. That's where I'm going to use this expression. So lambda v naught. And I think I'm almost there. Let's cancel out the things that cancel out. Pi cancels out. 2 cancels out 2. I'm going to divide both sides by d to cancel out d here. Then solving for b, I mean it is b, that's equal to 2k over c squared times lambda v naught over d. So this is my derivation of magnetic field using Ampere's law. Now I'm gonna follow my own directions here. So show the magnetic field, clean decline Amperian loop you're using, find the directional direction. So where necessary, give a brief word description of any figures. Yeah. So for the submitted answer, this is what I'm gonna do. Direction of magnetic field at the location of wire 2 is into the page. And in order to derive the magnitude as given, we choose an Amperian. By the way, a lot of people spell this with I. I never liked it. Amperian loop of radius D, using symmetry to pull B out of the integral in owing to B dot dl is equal to 4 pi k e over c squared I enclosed. Solving for B gives the magnitude of B. See attached work for figures and more detail. You should include some detail, so I have a way to anchor your attached work, which can be done at any time without time limit, into the answer you submitted within the time limit. Find the magnetic force per meter on wire 2 due to magnetic field generated by wire 1. So for this I'm gonna use force on current, magnetic force on current carrying wire is given by the magnitude of current times I guess dl, or well dl as a vector cross B. Yeah. So So I for that left side magnetic field pointing into the screen. So DL is up into the screen. So magnetic field is to the left. Uh, Applying the right hand rule with the cross product gives the leftward force on wire 2 due to wire 1. The magnitude of the force is F is equal to, so the rest is plugging things in. I, that's gonna be lambda V naught times, and it's per length, so so I'll say length times it's a 90 degrees, so I don't cross product, just gives you, regular thing. So magnetic field, which we already had, 2 ke over c squared times lambda v naught over d, dividing by length for force per meter. We have F per length is equal to all of this without the length. Yeah, I don't think I need to attach any work for part B. I'm basically putting everything here. Alright, I think I have 10 minutes left. I've been looking at the stopwatch. Find the electric force per meter between the two. Oh, okay. So here's where you can appeal to formulas you have memorized. So I'll say I have the formula for a line of electric field memorized, which is E is equal to 2 ke lambda over distance. So here E is equal to 2 ke lambda over d, that's the distance, and the force per meter, and the force per meter is F over length. Should be just linear charge density times the electric field, which would be lambda times 2 ke. So that first lambda is the charge density, and the second lambda is part of the formula for the electric field over d. Let's see. The direction on wire 2 is rightward, since like repels like, same positive charges repels. So with that, so for part D, what is the direction of the net force on wire 2 due to wire 1? So here's, I think, where it's nice to kind of write it out and simplify. So combining results in B and D, the net force is rightward being positive. That's how I'm gonna define it. So net force divided by length is it's gonna be this thing as a positive quantity minus the magnetic force, which was pointing to the left, so it'll be this. And I'll say I need to simplify this C attached work. I think I have time to attach do more work here, so let me write it out and simplify it this way. Kind of typing and simplifying, it's annoying. It's hard. It's not easy. Wait, where's my eraser? This is part D. So I have my net force per length is equal to, let me write down the first term. I probably should combine the lambda, because I see lambda squared basically. Divide by d minus lambda v naught 2ke. I'm gonna put all the numerators together. So lambda, oh wait, there's a v there. So 2k lambda v naught, and then all the denominators together, c squared and d. So I can simplify this a little bit, combine this lambda with that to get lambda squared. Combine this lambda v naught with that to get lambda squared v naught squared. And there are some surprising common factors. So factoring those common factors out, 2k, I think even lambda squared and d. So I have 2ke lambda squared over d. So this is 1 minus the right hand side term, 2k lambda squared over d. So I have v naught squared over c squared. So the question of direction comes down to, is this positive or negative? So let me just write down this much so far. Net f divided by length is equal to 2k lambda squared over d times 1 minus v. Let me put parentheses so it doesn't get confused. 1 minus v naught squared over c squared. If v naught is less than c, speed of light, and this is the matter where which seems likely, speed of light is 3 times 10 to the 8 meter per second. Then the net force is positive and directed to the right. Repulsive force between the wires. If v naught is greater than c, which for physical reasons you will learn later cannot happen, then the net force is attractive. Can the total force for the question, and since the question tells us to assume v naught less than c, this never happens. In fact, this question is a question that I like, which is why I was happy to do it at this session. This has connection to special relativity. So when you cover special relativity in Physics 4C next semester, hopefully, then you will be able to see that. So here, the force apparently depends on velocity, and that's frankly because we don't know enough of physics. There's a modification that enters into expression for lambda, 2 lambda through Lorentz contraction. It's a special relativistic effect that's gonna come up in Physics 4C. Once you include those special relativistic effect, then it turns out this dependence, it cancels out. So the net force between these two wires, it turns out it doesn't depend on whether they are moving or not. So the amount of force when they're stationary and the amount of force when they are moving, it's the same. And this is what I was talking about earlier when I was arguing with the ChatGPT about both the magnetic and electric force being inverse of square force. Through special relativity, those two phenomena are going to be related to each other, linked to each other. And here in this physical setup, the physical force in a direction perpendicular to the movement doesn't change. Whether you include the magnetic force or, like when you include the magnetic force, as long as you include all the special relativistic effects, net force doesn't change. Now, so that portion requires Physics 4C, so you're not required to add that explanation. And just adding that as an aside, that's something for those of you going to Physics 4C can look forward to. That there was something that you are learning this semester that actually had a very deep fundamental connection to special relativity that you will be hopefully learning next semester. So let me paste this in, and I can submit and show you the answer key just to make sure I didn't make any mistakes. I don't think I did, again, because this is a question I like, question whose details I remember very well. So I don't think I made any mistakes. But I'll show you the answer key just to be sure. And by the way, this question obviously isn't auto-graded, so I'm just gonna get 0% in terms of the auto-graded score. So it needs manual grading for correct assignment of points. Let me submit it then. I guess I had time left over. Alright, save work and continue. You know where to review work. And you can also, you know, change this if you want to. You know, if you refresh, you'll get a button for add work. So you can always do that. So, alright, let me bring in, I'm gonna log in as an instructor, and let me bring up test students attempt in my instructor view, and I will show you the question and the answer key so that if I made any mistake, here's my chance to correct. I don't think I did, but you know, here's my chance to make sure that I didn't make any mistake. So there it is, all this. So suppose that yeah, so this is my thing. As the wires move upward at speed of Vina, I guess I do give a more justification for the current. Yeah, sure. Model and so will always include more detail than you can reasonably include in 20 minutes. Amperian loop, yeah, so that's all the figures. Use the Amperian loop, go through this and get that, yeah. Right hand rule, yeah, into the page. Can I set it into the page? Yeah, good. Part B, the magnetic force per meter, wire can be yeah, with the amount of current, magnetic field that, so you use that to, yeah, magnitude only is that. Direction, using right hand rule, is left for wire 2. Yeah, so I think I did that, yeah. Electric force, you know, use the formula to the electric field times the charge density, and you get that, and it's repulsive. And part D, calculate the net force, and yeah, that's the aside. Okay, I swear I didn't look at the answer keys. It's just, you know, the question is actually written in order to demonstrate this. That's sort of the hidden main point of the question.